Okay, so now that we derive spherical coordinates, we can begin to solve a triple integral that looks like this. So this is a really complicated triple integral. And the reason why we would want to change this to spherical coordinates is, well, first of all, we notice that the regions of integration correspond to a circle in the xy plane. So this is described by this. And then to a sphere along the set axis. So basically this is just a spherical region of integration. So it makes sense to use spherical coordinates to solve it. And we have this expression here that we cannot actually integrate using Cartesian coordinates because you have a square root here. So there's no method that you can use to actually integrate this using Cartesian coordinates. So the first thing we're going to do is we're going to start with our xy plane. So we're going to take those two first limits. So we have x goes from -1 to 1 according to this, and then y is going to cover the following semicircle. So the first semicircle is 1 minus x squared, and then it's going to go to 1 minus x squared. And hopefully you can see that each of these semicircles has radius 1. So this is our x-axis or y-axis. So we have -1, 1 here, and then we have -1 and 1 here. So the entire region that is built from those two semicircles is just a full circle. So this is going to be a region of integration D. Now, what kind of expressions can we derive from this? Well, when it comes to spherical coordinates, there are two things that we can. There's just one thing that we can actually derive from this in terms of the limits of integration, and that is that theta is basically going to complete a full rotation here. So that's going to go from 0 to 2 pi. Now you could argue that, well, the radius here is going to go from 0 to 1. So you could write something like the radius goes from 0 to 1. But remember that this radius is not the same as the radius of the sphere. Not all the time. In this case it would be, but what we can do is we can now draw our three-dimensional space. So let's have x, y, and z. So our region of integration xy, that's just a circle here. So that's 1, 1, -1, and -1. And now the region of integration with respect to z, that's going to be two hemispheres rather. So it's going to cover this and that. So, and both of those are going to have radius 1. So hopefully you can see that now. So now that we have that, we know that, well, the radius of the sphere has to be equal to 1. So basically rho is going to vary from 0 to 1. So in this particular case, because the whole region of integration is a sphere, then this and that are going to be the same. But that doesn't need to be the case all the time. So that's what we can infer from this. So now that we have those limits of integration, of course, we need to find phi. So if we have a full sphere here, then that means that phi should go from 0 to pi. Because remember that phi is just basically this rotation here. Okay, so now that we have all those things, we can actually write this integral in terms of spherical coordinates. So let's do just that. We're going to organize this, so we're going to remember that the volume element is going to be rho squared sine phi, then d rho, d phi, d theta. And then we're going to start by, we're going to put the theta limits on the outside, so 2 pi. Then we're going to go for phi, so that's 0 pi. And then rho, 0, 1. Now what's the function that we're integrating? It's this function here. So when you want to relate this to spherical coordinates, you know that this is just going to be equal to the radius of the sphere squared. So this here is just going to be square root of rho squared, which is just going to cancel out. That's just going to be rho. And now you're going to multiply it by the volume element. So that's going to be rho squared sine phi d rho d phi d theta. So now that we have that, we can actually begin to integrate this. So first integration is going to be performed with respect to rho. So we're going to have 0 to 2 pi, 0 pi. And now we're going to have rho to the power of 4 over 4, because we're going to rho squared times rho, that's rho to the power 3 before we integrate, and now we have times sine phi. That's going to go from 0 to 1, and now we're going to have d phi d theta. So this is going to be equal to 0 to pi, 0 pi. So substitute rho for 1 and 0, so that's going to be 1 over 4. So 1 over 4 sine phi d theta. So I can move that 1 over 4 to the outside, so this is going to be 1 over 4 0 to pi. And now we want to integrate sine phi with respect to phi, so that's going to be minus cosine of phi, and we're going to integrate this from 0 to pi, and then d theta, and then we're going to have 1 over 4 0 to pi, and once you substitute for the limits there, you'll see that this should be equal to 2 d theta, so this becomes 1 on 2 theta from 0 to 2 pi, and then this becomes pi. So pi is the final answer for that really overly complicated integral that we looked at here. So this shows you that there are very different ways to perform triple integration, and spherical coordinates is really powerful for when it comes to very complicated expressions like this, which actually happen a lot in electrodynamics. Sorry, not electrodynamics, but electromagnetism in general. You will find a lot of expressions like this. So spherical coordinates can be quite handy for solving very complicated triple integrals like that. It doesn't mean that it always works, but if you can find some relations between expressions like this and spherical coordinates, it's a really good system of coordinates to use.